In this video we're going to look at moles and equations really related to masses and gas volumes and how we convert between one substance and another using a balanced equation. So we should be relatively familiar with our two equations relating moles to mass in grams and to volume in decimeter cubed. You may be familiar with them in terms of a formula triangle. I'm writing them like this to try and get you away from using a formula triangle or relying on it too much. So one of the problems with a formula triangle is if you try and rote learn it and you forget which way everything goes, you forget what goes at the top, then you are just going to get everything wrong from that point in the question, even if you know how to rearrange the formula. If you try and really think about what things in the formula mean, it's a lot easier to write the formula out in the different ways that it comes. So this is the way we would normally have it in the triangle, with mass in grams at the top, relative formula mass at the bottom, volume in decimeter cubed, and 24 decimeter cubed. Let's look at another way that we could write these equations out. So we could write them in terms of mass and volume. Now these are mass and volume that we measure. So when we say mass, we mean mass in grams, and that's basically our real life number. So it's what we measure in the lab. It's what we can put on a balance and say, oh, I have 1.2 grams of magnesium. The number of moles just tells us how many atoms there are in the magnesium, or how many molecules there are in the water, whatever it is we're measuring. And the mass of 1 mole, so I've substituted in the term mass of 1 mole instead of formula mass or MR, depending on how you write it. And that's because, well, really that's what the formula mass tells us. So if we remember that what we get from the periodic table, that is the constant thing. That is the thing that it's different for different elements and different compounds, but it's something that we get from the periodic table from a reference value. And then there's a relationship. And that's hopefully an obvious thing, because an obvious relationship, because if I said that the mass of 1 mole of magnesium is 24, and I got that from the periodic table, then it stands to reason that the mass of 2 moles of magnesium would be 48. And I get the number 48 by doing the number of moles, 2, times the mass of 1 mole, 24. Once I'm happy with that relationship, I don't need a triangle anymore. You don't use triangles in maths to rearrange equations. You know that if you want to work out number of moles, you take mass of 1 mole to the other side, you do mass divided by mass of 1 mole. Easy peasy. Volume, even easier. Don't need to look at a periodic table for volume. Do need to remember units, even more important, and that's because grams is the normal unit that we measure mass in a laboratory. We don't tend to weigh out kilograms or milligrams of anything, but with a gas we do tend to measure our volume in centimeter cubed, because we don't deal with such large volumes of gas. So we do need to remember that volume is in decimeter cubed, but we don't need to remember this volume of 1 mole, because the volume of 1 mole is always at room temperature and pressure 24 decimeter cubed, or if we want to remember it in centimeter cubed, that would be 24,000. So we need to be happy converting between decimeter cubed and centimeter cubed, dividing or timesing by 1,000. Other than that though, that 24 should be given in the question, and therefore we always know when to use it. As you progress into A level, you'll start to do calculations at different temperatures and pressures, and that's because that 24 is only constant at room temperature and 1 atmosphere pressure. So in the question it will often say the volume of 1 mole of gas is 24 decimeter cubed, room temperature and pressure. But you can see it's the same relationship. You've got the real life number, like what you measure in the lab, is equal to how many moles, how many particles you have, times by either the mass of 1 mole or the volume of 1 mole, which is a fixed quantity. For mass, it depends on the element or the compound. For the gas, it does not depend on that. For volume, it is just going to be 24 for any gas at all. So our example calculations, find the number of moles in 1.32 grams of propane. So I've been given a formula for propane. I want the number of moles and I've been given the mass. So my number of moles, which I'm going to write as nom, is equal to the mass that I've got divided by the mass of 1 mole, which I can often write as moom, or you may prefer to write RFM. So RFM, I've got 3 carbons, each weighing 12, I've got 8 hydrogens, each weighing 1, so the RFM, or the MR, however you want to write it, propane is 44. Adding that up, therefore the moles, this time I'm going to write moles rather than NOM, is 1.32 grams divided by the mass of 1 mole. So the most common mistake that people make here is dividing it the wrong way round, but having a think about what it means, that number 44 means that 1 whole mole of propane weighs 44 grams. So if I've only got 1.32 grams, I've got much less than 1 mole of propane. So my answer should be a small number less than 1. And indeed it is. It's equal to 0.03. Unlike probably the stuff you do in maths, we know the stuff we do in science often ends up with very small or very large numbers. Okay, finding the volume in centimetre cubed of 0.08 moles of propane gas. So this time I'm trying to find the volume, not the number of moles. So I'm trying to find the real life value, the measurement that I could take. So if 1 mole occupies 24 decimetre cubed, if you're stuck on the equation, just roll back and think, well, what would happen if it was 2 moles? It would take up 48 decimetre cubed. So what did I do? I did 2 times 24. So if it's 0.08, I'm going to do 0.08 times 24. So my volume, and this is in decimetre cubed, equals 0.08 times 24. And that equals 1.92 decimetre cubed, but the question is asking me to do it in centimetre cubed, so I'm going to then times by 1000 to get 1920 centimetre cubed as my answer. And then the last one is just a 2-step calculation, because I'm asked to find the mass in grams, but I'm given volume. There is no equation that directly links mass in grams to volume of a gas. So I need to go with the information that I've got first, which is the volume of the gas. From the volume I can work out number of moles, because number of moles is going to equal my volume in decimetre cubed over 24, which is the volume of 1 mole. So 216 is not in decimetre cubed, so I want to divide by 1000, and that will get me 0.216 decimetre cubed. I can now put that in my equation to tell me how many moles of ammonia there are in 216 centimetre cubed. Pop that in my calculator, I get a number that is in standard form, 9 times 10 to the minus 3. I can turn that into non-standard form if I want to, but there's no need to because we're in the middle of a calculation, so we can leave it like that. That's how many moles. I need to know mass, And remember, my mass is just number of moles times by the mass of 1 mole. So number of moles is 9 times 10 to the minus 3. It's going to be a small number because it's a small volume. The mass of 1 mole, maybe I've got my formula for ammonia there, although I will need to know that formula. NH3, go to the periodic table, add it up, it works out as 17 grams for 1 mole. So for 9 times 10 to the minus 3, I times it by 17. Calculator went wrong, there we go. And my answer is 0.153 grams. I'm not expecting it to weigh a lot. It's a small volume of gas. So what do we do when it's not the same substance and it's calculations involving equations instead? So we're using this equation here. It's got a reversible reaction arrow, but that doesn't really matter for the moment. It's got numbers in front, and I just want you to look at that and think about how much information can you get from that balanced equation. Assuming you had a periodic table and everything else, what does that balanced equation tell you in terms of the number of moles of each reactant? So we've got nitrogen and hydrogen, and then the product, ammonia. What does it tell you in terms of the masses? Can you tell what mass of one thing would react with the mass of the other? And what does it tell you in terms of gas volumes? So you might want to pause the video and have a think and see if you can write down all the information that you could work out just from that balanced equation. Like, what ratios could you work out? Okay. So the first thing the balanced equation tells me is simply that nitrogen, N2, reacts with hydrogen, H2, to make ammonia. But this topic is about amounts. So what does it tell us in terms of amounts? Well, in terms of individual particles, like molecules, it tells me that 1 molecule of nitrogen reacts with 3 molecules of hydrogen to make 2 molecules. So that's like individual particles. When I say molecule for nitrogen, I'm talking about 2 nitrogens joined together. That is 1 molecule. For hydrogen, it might look something like this. So there are 3 individual hydrogen molecules. Tells me a little bit about the bonding involved. And for ammonia, it tells me that there are 2 of these NH3 molecules. I'm not going to bother drawing like the dot and cross diagrams, but that gives us an idea of what the 2's mean, so 2 atoms bonded together, what the number in front means in terms of 3 molecules, etc. We don't deal with individual molecules in chemistry because they're too small to count, and we would end up with all of our numbers being in standard form, big standard form, all the time if we had to deal with counting individual particles. So instead we deal with moles. Mole is just one big number of molecules, 6 times 10 to the 23. You don't need to use that at GCSE, but you will use it a little bit more at A level. And that tells me, therefore, since they're proportional, that 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia. What else can I tell? Well, I asked you to look at gas volumes and masses. So if I now went to the periodic table, I could look at the mass of 1 mole, the RFM or the MR, of each of these substances. So for nitrogen, nitrogen weighs 28 because 1 nitrogen atom is 14. So I could also work out that 28 grams of nitrogen, how much hydrogen will that react with? Well, there are 2 hydrogen atoms, each weighing 1, so H2 weighs 2, but there are 3 of them, so it would react with 6 grams of hydrogen. If I work out the mass of NH3, it's 17, we used that in the last question, but there are 2 of them, and so it would make in total 34 grams of NH3. So I've got a ratio of masses as well, and we can just check that 28 plus 6, the mass of my reactants, equals 34, which it does. That's the mass of my product. What about volume of gases? Well, I could go with the volume of 1 mole like I did the mass of 1 mole. So I could say that this equation tells me that 24 decimeter cubed of nitrogen would need to react with 72, so that's 3 times 24, decimeter cubed of hydrogen, and that would make in total 48 decimeter cubed of ammonia. So notice these gas volumes are not conserved. Mass is conserved because mass relies on like the individual particles that make the atoms up, so you don't lose or gain mass during a chemical reaction. But volume can change, and we know that from when we did about Le Chatelier and equilibrium, and changes in pressure will affect the position of the equilibrium. And so I could simplify that even more and just say that 1 decimeter cubed of nitrogen would react with 3 decimeter cubed of hydrogen to make 2 decimeter cubed. So the ratio of the gases is exactly the same as the ratio of moles, because every mole of gas takes up the same volume no matter what gas it is. So I can get a lot of information out, and so we shouldn't panic when we get a mole calculation that involves lots of things, because we can get loads of information from the balanced equation. So the balanced equation is in the centre of this little flow diagram, and what this is just to help you visualise what steps you would take in one of these longer questions where you're given some information about one substance, for example in that last example maybe nitrogen or hydrogen, and you're expected to find out a different piece of information about one of the other substances in the equation. For example, if I had 34 grams of nitrogen, how many grams of ammonia could I make? Or if I had 10 grams of hydrogen, what would be the volume of nitrogen needed to react with that? So it's working from one substance into another, and for that we need to use moles, because moles is the thing that's in the balanced equation every time. So moles is the one constant at which we can measure all chemicals in moles, no matter whether they be solids, liquids, gases or solutions. We're not going to look at solutions today though, we're just looking at mass and volume. So the first step is to find the information in the question. So that you should be given either the mass of something, so we're going to call that the known substance because you know the mass of it. For example, it could say 17 grams of nitrogen, or it could give you the volume of a known substance, so it could say 10 decimeter cubed of hydrogen. So we have something that we know a number about, and if we've got a periodic table or we've got that value 24, we can calculate how many moles. So my second step, once I've found the piece of information I need, is to work out the moles of the known substance. So what I'm going to do is I'm going to assume that my volume is given in decimeter cubed and that my mass is given in grams. If it's given in a different unit, I will have to convert it into the right unit first. But assuming I have mass in grams, how do I get to moles? Well, I'm going to divide by the RFM, or the MR, the mass of 1 mole. If I've been given volume, then I'm going to divide by 24. No need to look at the periodic table for that one. So I now know the moles of whatever it is I've been told about, and the question is now asking me about the moles of something else, so I'm going to use the balanced equation to work out the moles of the other substance. This is the bit that people often skip or forget. So you need to look at the ratio between the known and the unknown substance. Unknown can be thought of as like the output. It's the thing that you're going to have to get the answer about. So perhaps you look at the equation and you see that you know the moles of nitrogen and you want the moles of hydrogen because you need to know mass or volume of hydrogen. So it would be a 1:3 ratio and you times by 3. But we'll look at that in the example. Once we've done that, we then know the moles of the unknown. So that would be my step 3, is use the equation to work out moles of the unknown substance, the thing that we are trying to work out. And once I have that, we now just need to check what the question wants. Does it want mass? Or does it want volume for my unknown substance? And I'm just going to reverse whatever step. So I'm now going to times by the RFM. If I want to know mass, instead of dividing, I'm going to times it. So if I worked out I had 2 moles of nitrogen, I wanted the mass of nitrogen, I would times it by 28, which is the mass of N2. Notice you need to make sure that you're timesing by the RFM of the second substance here. You can't just put the first value in again, it won't work. If you've got gas though, it's nice and easy. All I need to do is times by 24, because it doesn't matter what sort of gas it is, what the formula is, they all take up 24. And that again is assuming that I want my answer in grams or in decimeter cubed. So let's put this into practice with some examples. Let's have a look at this one. What mass of sodium is required to produce 70 centimeter cubed of hydrogen gas when reacting with water? If you're confident, you might want to stop the video here, try writing a balanced equation for this reaction, and then seeing if you can do the calculation. If you're not, stay with me and we'll do it together. So, mass of sodium, hydrogen gas reacting with water. First thing I need is, I'm going to do the balanced equation first, even though I don't need it just yet. It probably would be given me in a question, but since this isn't about balancing equations, it's about calculations, I will write it out. And if that's what was stopping you from doing the calculation, you may now want to pause the video and see if you can do it. Okay, so mass of sodium, that's my unknown, I don't know, it says what mass of sodium. 70 centimeter cubed of hydrogen, so that's my known thing. I know that I have hydrogen and I want to find nitrogen, so I'm underlining them because I can actually ignore everything else in the question in that balanced equation. So what do I have? Well, I have the volume of a known substance in decimeter cubed, and I want to know the mass of an unknown substance. So that you can see which direction I'm going in. I'm going to go to here, I'm going to go through balanced equation, and then I'm going to go here. So those are my steps that I'm going to follow. So decimeter cubed, well, I haven't got decimeter cubed, I've got centimeter cubed. So first step is going to be changing centimeter cubed into decimeter cubed by dividing by 1,000. So 70 over 1,000 is 0.07 decimeter cubed, and that's my hydrogen. Next thing I do, I've got it in decimeter cubed, so I'm going to divide it by 24. So I'm going to work out my moles of hydrogen, and that's 0.07 divided by the volume of 1 mole, which is going to equal a pretty awkward number. So we have 2.917. I'm going to leave it 4 sig figs, which is quite a lot. However, I'm going to leave it like that simply because I don't want to round up too much too soon. As it is though, I don't need to put like 7 decimal places. 4 significant figures will ensure that you don't lose too much information, and then maybe we'll put it to 3 significant figures at the end. I've left it in standard form because it's much easier to see the significant figures that way. You could write 0.002917 if you want. That's my moles of hydrogen. So I've got as far as here, moles of known substance. So now I check the balanced equation. Well, there's my hydrogen. That's what I know, that I have 2.917 times 10 to the minus 3 moles. There's my sodium. Well, sodium has a 2 in front and hydrogen doesn't. So there are 2 moles of sodium for every 1 mole of hydrogen. So to get moles of sodium, I would take my number of moles of hydrogen and I would simply times it by 2. And this is where I left my number in the calculator because it's nice and easy to do that way. And so I got 5.833 times 10 to the minus 3 moles of sodium. If you round it up and then put your number in the calculator, you might have got those slightly different. It's not going to make a difference by the time we round up at the end. So I've got my moles of known substance. I'm now going to work out the mass of the unknown substance, which is sodium. I've got number of moles. Periodic table tells me the mass of 1 mole is 23. So my mass of sodium is going to be number of moles. Again, I've left it in my calculator, which makes it easier, times by 23, and that equals 0.134 grams. I'm going to leave it at 3 significant figures. A sensible number. It's a relatively small volume of gas, so it's a relatively small mass of sodium that's required to make that. And sometimes people go, well, isn't it 46 grams because it's 2 Na? Well, the thing is, I already used my 2 in the equation. I already used it here when I times by 2. And both of them would work mathematically. So I could either times it by 2 and then times it by 23, or I could times it by 46. I want you to get used to doing this method because it works for volume, it works for solutions, and it works for masses, and it doesn't matter. So using the balanced equation method is going to help you in the long run with being able to do more complicated examples. Okay, second example. What volume of oxygen would be needed to completely combust 4.56 grams? So here's some known information of octane, and I've got a formula. And what I want to know is volume of oxygen. So this time I've got a mass of known substance, so I can work out moles, use the balanced equation, moles of my unknown substance, and then work out the volume of my oxygen. Okay, so I know mass in grams. I'm also going to need a balanced equation. So again, if you want to write the equation, because we've had some practice balancing equations, you might want to do that. If you want to have a go at the whole question on your own, pause the video and then you can stop and fast forward and see if you get the same answer. Let's do the equation first in case we're not given it. So C8H18, I'm going to react that with oxygen, and I'm going to make CO2 plus H2O. So I'm going to do my carbon dioxide first, that's 8. I'm going to have 9 water molecules because there's 18 hydrogens. That's going to give me 16 plus 9, so that's going to give me 25 oxygen atoms. Oxygen goes around in pairs, so I'm going to do 12.5 as my moles of oxygen. I'm just going to rub that out so it's a bit easier to see. Now, nothing wrong with doubling it, as I've said before. So if you wanted to do 2, 25, 8, 16 and 18, you can for your balancing numbers. I'm going to leave it at that and show you that the maths, it doesn't matter if you have it like that, the maths still works. It should give you the same answer, so it's not a problem. Okay, so we've got a mass in grams, we've got 4.56 grams, and we've got octane. We need to work out the RFM of octane, C8H18. That's my first step because I've got a mass in grams. So putting it in, 8 times 12 plus 18 gives me an RFM of 114. So I can now work out my moles, because my mass is already in grams, so I don't need to do any conversions. My moles of octane is going to be the mass that I've got, 4.56, divided by the mass of 1 mole, 114, and that's going to give me a very neat 0.04 moles, a bit tidier than the last time. Okay, so that's my moles of octane. Now it's time to look at the balanced equation. So here is octane, I forgot to underline them earlier, and oxygen is the other thing I'm worried about. So it doesn't matter what side of the equation things are on, it's the numbers in front that are important. There's no number there, so that tells me that 1 mole of octane reacts with 12.5 moles of oxygen. So therefore I can now work out my moles of oxygen. It's going to be number of moles that I've got, 0.04, times how much, times how many moles reacts with that, so 12.5 times as much oxygen as octane is needed. 0.04 times by 12.5, and that gives me exactly a half, 0.5 moles. So if you'd done the balancing the other way, it still wouldn't matter, because your ratio would then just be 2 to 25. So you'd still do the same thing, you'd divide it by 2 and then times it by 12.5, then times it by 25, just the same as timesing by 12.5. Okay, moles of oxygen is 0.5. My last thing I want is volume. 1 mole takes up 24, so my volume of oxygen is going to be how many moles I've got, 0.5 times by the volume of 1 mole, 24. That's going to give me 12 decimeters cubed, and that's it. In this last bit of the video we're going to look at percentage yield, slightly different, but most of the calculation is exactly the same as and using that little flow chart that we used before. Percentage yield is generally, especially at GCSE, done just using masses. So we know the mass of a substance, we know we can work out the moles, we can work out the moles of something else, and we can work out the mass of our unknown substance. The difference is for percentage yield, you're working with this formula. So percentage yield equals my actual mass, so how much mass I got out from a reaction, divided by a very beefy phrase here, theoretical maximum mass, times by 100, because it's percentage. So when you're doing percentage yield, how does that relate to what we've just been doing? Well, the mass that we get at the end, this mass of the unknown, is always our theoretical maximum mass. So when we just did a calculation and said, oh, this is what volume of oxygen, or this is what mass of sodium would be needed, that's the maximum mass that would be needed to react with whatever it was that we had. So then we compare it with a mass that we've actually got. So the awkwardness here is that there are 2 masses in the question. There is 2.12 grams of sodium carbonate. There's something about sulfuric acid, but it says excess. Obtained a mass of sodium sulfate crystals of 2.02 grams. Calculate the percentage yield. So, just going to get that out of the way. We'll come back to it so that we can do this calculation a little bit better. So, with a little bit more space. 2.12 grams of sodium carbonate, that is my kind of known value. That's the thing I'm going to work with, and that's because that's what I reacted at the start. Obtained, I'm going to use that at the end. So that 2.02 is going to be needed not until the end of the calculation. So what I have got is the mass of a known substance. If I wasn't given it, I would definitely need the balanced equation. It would be pretty mean if they didn't give you the balanced equation for this. They also wouldn't do that because it would mean they'd have to give you lots of error carried forwards and things. So because this is not about writing equations, let's do a balanced equation for the reaction. Sodium carbonate plus sulfuric acid gives me sodium sulfate plus CO2 plus H2O. And I haven't been told anything about waters of crystallization. That will come up in the practice calculations, but don't worry. I'm assuming we're working out the mass of sodium sulfate. So that's what I want to know, because that's what I've been told here. This is my actual mass. I want to work out my theoretical mass of sodium sulfate. And I've got the mass of sodium carbonate, and I can see they're a 1-to-1, which is very useful. So I've got mass in grams. I want to work out the relative formula mass, or RFM, of Na2CO3 so I can work out moles. Add it all up, it so happens that it is 106. So from that I go into my next step, which is working out moles of the known substance, which is sodium carbonate. Moles of sodium carbonate therefore is going to be the mass that I've got, 2.12 grams, divided by the mass of 1 mole, 106. And that equals a very nice even 0.02 moles. Checking the equation, they are 1-to-1, so 1 mole of sodium carbonate makes 1 mole of sodium sulfate. So therefore my maximum moles, I'm just changing the wording, but it's the same process that I went through before, of Na2SO4 equals 0.02. They're the same. I've now got moles of my unknown, so I can work out the maximum mass. So before we just called this the mass because we weren't told anything about how much mass was actually obtained. So my maximum mass is going to be moles, 0.02, times by RFM. Need to do a stop here and work out the RFM, the MR, mass of 1 mole of sodium sulfate, because it's not going to be the same as sodium carbonate. Little check on the periodic table, and my calculator tells me the mass of Na2SO4 is 142. Times that by 0.02, and that gives me 2.84 grams. So that is my maximum. That's the most I could get out if it was 100% yield. Not normally 100% because we normally lose stuff while we're filtering and crystallizing and all the other stuff we would do in this experiment. So my percentage yield, which I've just got space to do over here, is going to be my actual mass. Got to go back and get that. Make sure that you get the actual mass given in the question, divided by the maximum mass, 2.84, times by 100, and that gives me an answer of 71% yield. Percentage yields are normally, more than 50, unless the experiment's really, really bad. So they should be relatively large numbers.